in example 2, we are going to examine a power series. The series n goes from 1 to infinity, x minus 1 to the n over n, that approximates some function f of x, and we would like to find the interval of convergence of this series. But before we go ahead and compute the interval of convergence, let's examine approximations by a 2nd degree, 6th degree, 10th degree, and 14th degree power series. So for at x equals 1, the series and the function are equal to each other. But then what happens as we go away from 1? It looks like the 2nd degree polynomial shows that, yep, for a little while we have pretty good agreement. And the 6th degree shows even more values of x, where the red approximation and the dotted graph of the function are very close together. And the 10th degree polynomial, we get even a little bit more values of x. So it almost looks like when we go to anywhere from 0 to 2, we have pretty good agreement. But outside of that range, we have a gap appearing. And the 14th degree polynomial is showing a very similar picture. So we have pretty good agreement where I'm drawing right here from 0 to 2. But then outside we have this gap. So maybe a good guess would be for our interval of convergence that it works for values of x. We get convergence for values of x between 0 and 2. Now let's go ahead and see if we are right. Let's find the interval of convergence computationally. And we are going to start, just as in example 1, we're going to start by looking at the ratio test. And the ratio test tells us to look at the limit as n goes to infinity of an plus 1 divided by an in absolute value. Okay. For this particular series, an, I'm circling it here, right here. This is an. And so we get limit as n goes to infinity, an plus 1, that is x minus 1 to the n plus 1 divided by n plus 1. And then we need to divide by an, and just like we did in example 1, instead of dividing by a fraction, we can multiply by its reciprocal. So that is n divided by x minus 1 to the n. Now we need to simplify. And we can see again that if we regroup our x terms, we have a lot of common factors. We have x minus 1 to the n plus 1 over x minus 1 to the n. Most of those are going to cancel out, and what we are left with is x minus 1. And since that doesn't involve n, we can factor that out and pull it out of the limit in absolute values. So we have the absolute value of x minus 1, and then we have the limit as n goes to infinity of n over n plus 1. And I can drop the absolute value here because n and n plus 1 are always positive anyway. Now, how do we compute a limit like this? One tool that has worked in the past, and that works here, is L'Hopital's rule. So if I use L'Hopital's rule, I get the limit as n goes to infinity of the derivative in the numerator, that's 1, the derivative in the denominator, that is also 1. And so my result is that this limit on the ratio test is just the absolute value of x minus 1. And so this is the value of r in the ratio test. Now what does that mean? We wanted to know for what values of x does our series converge, and the ratio test says this happens when r is less than 1. So we need x minus 1 in absolute value to be less than 1. We can rewrite this. We can drop the absolute values and write this instead as well, I wanted to drop the absolute value. Let me do that. We can write this as x minus 1 is less than 1, but it's bigger than minus 1. So whenever x minus 1 is less than 1, the absolute value is less than 1, but also we need x minus 1 to be bigger than minus 1. So these two inequalities are equivalent. They say the same thing. And now we can rewrite this one more time. We want to know for what values of x do we get convergence. So I would like to solve this inequality for x. And I can do that by adding 1 everywhere. So adding 1 gives me 0 is less than x is less than 2. So just like we were estimating in part A, we were guessing that our interval of convergence goes from 0 to 2. This seems to confirm it. So we see that the series converges for 0 less than x less than 2 by the ratio test. But what happens at x equals 0 and x equals 2? What happens at the endpoints? Well, if we plug x equals 0 and x equals 2 into the absolute value of x minus 1, we get 1, and so the ratio test is inconclusive. So at x equals 0 and x equals 2, the ratio test gives us x minus 1 is equal to 1, so that's inconclusive. So we can't use it. We have to examine the endpoints separately. So let's do that. Let's look what happens at x equals 0. And let's remember what our series was. Our series is n goes from 1 to infinity, x minus 1 to the n over n. So that is 0 minus 1 to the n over n. That simplifies, or I can rewrite that as minus 1 to the n over n. That looks nice. That is an alternating series. With bn equal to 1 over n. So that we can handle. Let's look at what happens at x equals 2. When I plug in x equals 2, I get n goes from 1 to infinity of 2 minus 1 to the n over n. And that is the sum n goes from 1 to infinity of 1 over n. And if you remember, this is a divergent p-series. So this is a divergent p-series with p equals 1. So we can now examine these two series and come up with conclusions. So at x equals 0, we had an alternating series. And does it converge by the alternating series test? Well, let's check real quick. So at x equals 0, the alternating series, well, let's see, does it converge or diverge? We need bn to go to 0, which it does. Bn goes to 0. And we need bn plus 1 to be less than bn. So 1 over n plus 1 is less than 1 over n. So yes, actually at x equals 0, the alternating series obtained how am I going to say this? The alternating series obtained converges. Because we have the limit as n goes to infinity of 1 over n is 0, and 1 over n plus 1 is less than 1 over n. So the alternating series converges by the alternating series test. Okay, great. Now, what happens at x equals 2? At x equals 2, the p-series obtained diverges, since p is equal to 1, and we know by the p-series test that we get divergence in that case. So what's our final conclusion? I'm almost running out of space, so our conclusion is the following. Our interval of convergence well, we already know it goes from 0 to 2, and since we get divergence at 2, 2 is not included, and since we have convergence at x equals 0, we get convergence at 0, 0 is included in our interval of convergence. Another way to write this would also be 0 is less or equal to x is less than 2. So that's another way to write it. And if we wanted to draw it on the number line, so here we have 1 right in the center, and then at 2 we have an open interval, and at 0 we have the closed interval. So our interval of convergence is everything including 0, but excluding 2. So you can also visualize it like that.